Hi everybody, welcome to Video Notes 3A. We're going to look at energy and states of matter. So let's get busy. Here's our first objective, being able to describe and explain the relationship between energy content and how particles are arranged and how that can change. So we got to see how energy is stored and how energy is transferred. We also have to be able to draw and describe changes to a system as energy is added or removed. Okay, so we're going to do bar charts, we're going to do heating and cooling curves, we're going to look at states of matter and temperature and phase changes. Okay, so arrangement and attractions of states. Solid have the most attractions and often in many directions to give regular patterns. So this is a representation of a solid. And those two are attracted, and those two are attracted, and those two are attracted. And so you have this regular arrangement of particles that you could see. And then guess what? You could see it again, right? The regular arrangement of particles. You could see it again. It's a repeating arrangement because they're attracted all around to the molecules that are close, okay? Liquids have less attraction, okay? If you look at the arrangement, it's a little bit iffy. It's not a set pattern because there's less structure and they have less attraction. They still stay really close, though. These are pretty close. I mean, that's close. This is close, and that's still close. All right, gases have and it's because they still have attractions for each other, okay? But it's not in a regular pattern. Gases have virtually no attractions. They spread out and are mostly empty space. So these gases don't even know these other exist. They're like, whoa, no one's around. Boom, can't run into them. I'll just bounce back off, okay? So if you want to change a solid, you have to overcome the attractions that everybody's having. If you want to change a liquid, you have to overcome the attractions. A gas has already done that. So looking at motion of particles again. See, they're moving. Can you see them moving? Now, this is a model, but I want you to see that every time you look at a solid, it's not static. It's always moving, okay? Liquid, you could see the translational motion. So solids vibrate, so it's vibrational motion. Vibrational, all right? Liquids also have vibrational, but look, they can move around each other. That's translational. And then gases have lots of translational motion with the space in between them. Okay, so you have to picture this when you picture particles. All right, so energy of the state is the energy that makes them what state they are. So this one where it says ECH, we're not going to do that one for now. That's chemical energy. We're just going to look at the thermal and phase energy. So energy of state is phase. Now, I know you think of this state, woohoo, right there, and this alpaca wants to go. Energy of state is the phase, EPH. Solids have the lowest energy of phase, so their phase energy is going to be 1 bar. So 1 bar is going to be their energy of phase. Liquids, a little bit more energy than solids, so it's going to be 2 bars. Okay, so that just shows they have more phase energy than the solids. Gases, though, have a ton of phase energy, so we're going to do 4 bars for gases. Okay, so if you're doing a diagram for energy, a bar graph, a bar chart, just keep those in mind. Solids 1 bar, liquids 2 bars, gases 4 bars. Okay, so what happens to particles when energy transfers in? So if energy is coming in to the particles, that energy can make the particles move faster. That's their thermal energy and their energy of temperature, and they start moving faster. Okay, look at not so fast, faster, faster, faster. But notice it's same state the whole time. Okay, just the molecules in that state are moving faster. This represents liquid. Okay, now what else can happen when energy transfers in? Okay, so ETH can go up. That's thermal, and that's motion, and that is temperature. Okay, thermal, motion, temp. Also, state can change. So solid can change into liquid, liquid can change into gas, and that's the EPH can go up. So that's energy going into a system can do that. All right, phase. So when the phase is changing, these attractions have to be overcome. And so now they can move around more. They still have attractions, but they can move around and have translational energy. And then overcoming all of the attractions gets you a gas. Okay. So what happens to particles when energy transfers out? Well, exactly the opposite. But if energy is transferring out of your system, okay, then the particles in the system will slow down, okay, or they can go to a state with more. So E thermal can go down, and that means temp goes down, and they could stay in the same phase, or the E phase, the energy of the phase can decrease, and so then it can turn into from a gas to a liquid to a solid. Okay, so this is the phase energy changing. This is the thermal energy changing. Okay, I knew that's what they were doing. Okay, so thermal energy again, ETH, energy of moving particles, energy of temperature or changing temperature. Keep that in mind. ETH is temperature moving energy. Okay, so I had ice in my soda, and it goes from 20 degrees to 4 degrees Celsius. All right, so here's the system. Here's the drink, the soda. All right, so when we got to look at the start, so how much E thermal does it have? Well, we're just going to say, well, just put 20 degrees about there. You don't really need to have it, but we just know, okay, it's got some, right? Right. And it's a drink, so it's liquid. So how many bars for liquid? Well, our E phase is going to have 2 bars because 2 bars for liquid. Okay, so 2 bars for liquid. And then it's at 20 degrees, so it has some energy of motion and energy of liquid. Okay, so if your drink, in order for the temperature of a drink to go down, it has to lose energy. Bye-bye energy, all right? So then initially we have this much energy, and the temperature goes down. So let's just say it goes down to like about here, all right? Okay. So the energy went down of thermal, okay? But what about phase change? Well, it's still going to be liquid at 4 degrees Celsius, so the phase energy doesn't change. Okay, so you can see the changes. We know that energy is lost. Where's that energy lost from to go into the surrounding? It's from the thermal energy, so the particles are moving slower. All right, I put my hot chocolate in the microwave and it goes from 20 degrees to 85 degrees. Well, I think you just put your chocolate in the microwave because it's not hot yet. Okay, nice try, I know. All right, so it goes 20 degrees to 85 degrees. So here's our cup of hot chocolate. I'm going to put cocoa. There's our cocoa. All right, so let's see. At the beginning, it's 20 degrees, right? Our E thermal is 20 degrees. This is the temperature one. So we'll give it 2 bars. We gave it 2 bars up there. I mean, it doesn't really matter. It's just we're going to compare it to when we're done. E phase. So it's going to be a liquid when it starts. So that's 2 bars. Liquid's 2 bars. Okay, so if it's going to get hotter, heat has to flow into my hot cocoa to make it nice and toasty warm. All right, so what's going to happen to E thermal? Well, the temperature goes up. All right, temperature goes up. But what state of matter is it's still liquid, so I only have 2 bars there. So the energy change caused the particles to move faster when the energy transferred in. So our initial energy to our final energy, there's more in the final. And it's in the form of thermal energy because those particles are moving faster. Cup of hot cocoa. Ooh, look at this hot cocoa cup. Yay. Oh, there's a marshmallow. Okay. In the winter, the air temperature fell from 5 degrees Celsius to negative 20 degrees Celsius. Ooh, that doesn't feel good. All right, so when we first start, we're talking about air. All right, air is our system. So 5 degrees we started with. All right. So it's about 5 degrees Celsius. All right. And air. What's air? Air is a gas. Woohoo, a gas. 4 bars. All right, 4 bars for a gas. So the phase of a gas has 4 bars worth of E phase energy stored in it. All right, what's going to happen to this air? Well, the temperature falls, so the energy's got to leave the air. Goodbye, energy. All right, what's going to happen to E thermal? Well, it's going to go down. All right. Oh, that's very cold now. Look at that small E thermal bar. Those molecules are moving so slow, but guess what? They're still gas. They're still gas. So the phase energy actually hasn't changed. It's still 4 bars. 4 bars. Okay. All right. This is kind of fun. I hope you're having fun. All right. On January 4th, the snow was negative 15 degrees Celsius, but on January 5th, the snow melted and it was 20 degrees Celsius. So here's our snow. Right? Snow is solid ice. So when we first started, it was negative 15. Okay. So let's just say that's cold. So those particles are vibrating in their solid form, right? E phase. So this is snow is solid. How many bars for solid? Our E phase is 1 bar. Okay, 1 bar for solid snow. All right. What happens to the snow to make it melt? Well, energy has to transfer in. All right, energy is transferring into the snow. So from initial to final, it has to go up. Does the temperature go up? Yeah, it goes up. So it went from 5 degrees to 20 degrees. I'll put it like that. All right. But what happened to our snow? Well, snow turned into melted snow, aka H2O, liquid. All right. So we did change our phase in this one, and we need 2 bars because 2 bars is liquid. So we could see that the energy coming into the snow increased in thermal energy because the temperature went up, and it increased in phase energy because the solid turned into a liquid. All right, so melting takes heat in. Yeah. Okay. So what kind of data do we need to know to predict the kind of energy changes that are going to happen? Well, we need to know the substance, and we need to know its melting and boiling point. Okay. So there's some data for that. You'll get to use that data. Okay. So this is the temperature when benzene turns from a solid to a liquid. Or if it's cooling down, it'll turn from a liquid back to a solid. If it's cooling down, right? And then at 80 degrees, the liquid will turn to a gas if it's taking in that phase energy, or the gas will turn back into a liquid if it's losing that phase energy. Okay. Oh, look, it's a heating curve. Yay, we love heating curves. I heart heating curves. Heating curves. Okay, I know that's silly, but it's fun. All right. So this temperature where you see a flat line, this is going to be the MP, the melting point. And then this temperature is going to be the boiling point. This is generic, so this could represent any substance, because any substance that starts as a solid, it's going to be a solid here, it'll be able to turn from a solid to a liquid when its phase is changing at its melting point. It's going to be a liquid here, so that its E thermal can change. Right? Here's where its E phase can change. Here's where its E thermal can change. And then liquid can turn to gas, and this is another place where the E phase can change. And over here we have all gas, and so the E thermal can change. Right? So this happens to every substance, that if we took it from a solid to a gas, it would have this kind of graph. Okay? Look! Particles, 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 to give you an idea of what's going on. Solid particles vibrating here, vibrating more, 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 until they can start to overcome their forces. And so we're going to get a phase change here. All right. But this is a E thermal. Over here we have a temperature change where it's all liquid the whole time, and more thermal energy. So they're moving faster, 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 still liquid, but now every particle can change from a liquid into a gas. But notice what happens to the temperature. The E thermal is not going up because all that energy is breaking those bonds, okay? And then we can have E thermal again when it's a gas, a change of E thermal. Okay, so I'm going to call these the slanty parts. Slanty parts. See slanty? Slanty are E thermal. Flat parts, flat. Flat parts. I know, that's fun, right? The flat parts are phase changes. Slanty parts are thermal energy changes. Okay, so we get to make a heating curve for a substance called yum. So this is yum. Yum melts at 155 degrees Celsius and boils at 210. Okay, so here's a heating curve that represents a whole thing, but we're not on this whole heating curve yet. We got to make it. So what do we put on the temperature axis? We put 210 degrees Celsius and 155. So you always put the temperatures given in the problem. All right. So what is it before it melts? It's a solid. As it's melting, the solid's turning to a liquid. And then from 155 to 210, it's a liquid, and then starts to boil. All right, so then the liquid turns to gas. Notice this is usually a longer bar. After that, it's a gas. Okay, so why do you think it takes more phase energy? Here's E phase again. Here's E phase. Why is the E phase bar from liquid to gas longer than the energy of phase change from solid to liquid? All right, so longer. Why? Why don't you think about that? We'll talk about that in class. All right. But remember that when a solid turns to a liquid, you only have to overcome the forces making it have a pattern. And now it doesn't have a pattern. Here, it's moving around pretty close, and you got to make it turn into a complete separation. Okay, so to review, energy of moving particles is ETH. That has to do with temperature and motion. Okay, so that's temperature. So when temperature is changing, ETH is either increasing or decreasing, depending on which way the temperature is changing. Energy of phase is EPH. So when phase is changing, EPH is changing. Solid gets 1 bar, liquid has 2. Woo, hoo, hoo. 1, 2. Whoops. And gas has 4. What? 1, 2, 3, 4. Look at all those bars. Whoa! All right. Heating or cooling curves need temperatures and lines. Slants are ETH, and flats are EPHs. If it has both, it has both. And know what particles are doing on each slant or flat. All right, that's it. Thanks for playing. Remember, I just put the objectives at the end to see if you can talk through those. Take good notes.